Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for joining today's webinar, Remote Radio Heads in Today's Evolving RAN Environment, sponsored by Rohde & Schwarz. Our presenters today are Craig Stanziano, President, Distributed Wireless Group, Jeremy Klein, Applications Engineer at Rohde & Schwarz, Roger Pahe, VP of Product Strategy at Absolute Analysis, and moderated by Olga Yashkova Shapiro, Program Manager, Communications Test Practice at Frost & Sullivan. Just a general overview of today's webinar. We will start with a market overview from Olga. Then we will go on to more of a remote radio head technical overview from Craig. After that, we will be followed with an installation and test of remote radio heads in the field presented by Jeremy and Roger, and then we will go back to Olga for conclusions. At the end of this, we will have a Q&A section, so if anyone has any questions, again, please submit them via the control panel. At this time, I'd like to pass the presentation over to Olga.
Thank you, Kyle. Welcome to today's Evolving RAN Environment webinar. If you can, Kyle, move to the next slide. In this presentation, I would like to talk about network densification and what drives it. I will look into small cells and headnets, as well as 5G technology, and also take a glance at what the wireless networks of tomorrow might look like. Moving on to the next slide. Mobile wireless communications experienced explosive growth over the last 10 years, fueled by the popularity of smartphones and tablets. The industry has taken on the challenge of supporting a 1,000-fold increase in traffic demand over the next decade. Operators are looking to lower the number of devices and users per cell, especially in high traffic areas, to address the overwhelming growth in mobile data. This is where the term densification of networks comes into play, as it means increasing number and variety of base station and access points such as NODs, small cells, and relays. According to Cisco's Visual Network Index, global mobile data traffic grew 69% in 2014. It reached 2.5 exabytes per month at the end of 2014, up from 1.5 exabytes per month at the end of 2013. And by 2018, this number is expected to exceed 24 exabytes per month, and this is pretty significant. Moving on to the next slide. Advanced networks, new form factors, faster processors, sophisticated screens, and support for innovative multimedia applications, all those equal to staggering mobile data consumption. By looking at North American market, and specifically market share by type of connections, we can clearly see that the share of smartphones as well as M2M connections is increasing. So the total number of connections on Tier 1 mobile operator networks expected to increase from 300 million in 2011 to almost 380 million in 2017. So this represents a CAGR of approximately 4% from 2011 to 2017 for that time period. In 2011, just interesting to compare, feature phones accounted for 46.6% of the total share, followed by smartphones at only 38.4%. So those two were the top two mobile device types on Tier 1 mobile networks in the United States. In 2017, smartphones are expected to account for at least 64%, followed by M2M connected devices at 17.2%. So those two could be the top two device types. From this, we can clearly see that smartphone connections are expected to dominate the market going forward. Moving on to the next slide, please. Frost & Sullivan expects there will be more than 100 million active LTE connections, such as phones, mobile computing products, and M2M in the United States by 2017. So we all know that LTE devices expected to consume anywhere from 2 to 4 times more data compared to 3G or 3.5G devices of the same family. So when including Wi-Fi usage, LTE results in an uplift of 5 to 10% for average monthly data consumption for smartphones. Difference in LTE and non-LTE data usage is most apparent in larger screen devices where multimedia applications tend to dominate mobile data consumption. Next slide, please. Smartphone users spend nearly 80% of their daily device use time on non-voice activities. Traditional capacity expansion is just not enough anymore. Mobile data traffic will continue to grow exponentially and will not be met by traditional network growth. Operators will increasingly look to small cell solutions such as Wi-Fi, femto, pico, offloading as a cost-effective alternative solutions to manage the rapid growth in data. And wireless offload strategy are expected to play a critical role even after the full migration to the LTE technology. The heterogeneous network or HETNET approach is expected to play a significant role in future mobile networks in order to improve coverage and capacity. Hyperdense deployment of small cells is expected to increase the capacity of network and extend the coverage outdoors as well as indoors. Small cells are expected to increase the capacity for outdoor coverage by placing macrocell coverage outside of residential buildings that have deployed small cells. An ongoing challenge with mobile wireless capacity makes small cells an attractive solution for network expansion. Moving on to the next slide. One of the main trends in radio access network, or RAN, is an interconnection of systems that enable network densification. Today, communication service providers have more options than ever before for the means of providing service to their customers. Together with the evolution of wireless standards, in order to provide higher spectral efficiency, vendors introduced a wide variety of radio access nodes. While the macrocell still remains the main mechanism, small cells, distributed antenna systems, distributed radio systems, remote radio heads, and centralized RAN, C-RAN, also referred as a cloud RAN, are systems that will see increasingly wider deployment in the future. By looking at small cells, there is a clear trend in increasing their capacities. The number of small cells deployment is also increasing very rapidly. Small cells today are required to support multiple technologies, including Wi-Fi, as well as multiple frequency bands and a greater number of users. This trend is not new and is only an extension of what has taken place in small cell development. Today, there are multiple architectures for small cell networks, which vary depending on the deployment scenarios. While small cells are gaining popularity in the indoor small venue market, DAS systems have been extensively deployed in the larger venues. There is also a movement that aims to provide a possible business case for medium-sized venues as well. There's also another school of thought that focuses on improving the economics for large venues where DAS is the dominating technology. This includes supporting greater number of carriers by enabling wider bandwidth over fiber, supporting new bands such as 2600 megahertz, and features such technologies as MIMO, which severely taxes DAS deployment. Another important development is enabling DAS to carry CPRI signals from a base station baseband unit over fiber to the DAS remote module, which reduces cost as it eliminates the need to radio at the feeder base station and related RF issues. Moving on to the next slide. Here we see the evolution of cell sites. Mobile operators are aggressively and proactively leverage advanced optimization technologies to ensure better and reliable coverage. They are identifying gaps in coverage and dynamically determining bandwidth needs, as well as optimizing networks in real time for efficiency. And this image is representing the migration of cell tower technologies to support higher bandwidth services in an efficient manner. So we can see that the radio access network is changing, and it does require new and evolved test equipment, which is no doubt. When you look at the far left side of this slide, you see the copper RF cable going from the base station up to antenna, and you test and measure return loss of that cable or distance to fault when it's switched out to fiber, and the antenna and remote radio heads together up in the air, and no longer you have to measure that RF cable run. And all of a sudden, these things start looking towards CPRI, and you move into the distributed antenna system. So already demonstrated the evolution of test equipment as well. For decades, the cell site architecture remained unchanged. However, as cost and efficiency started becoming very important to wireless operators, the time has come for an alternative. An alternative solution is a distributed base station in which the majority of base station equipment is located in an enclosure at the top of the tower near the antenna. This separate but integrated RF unit is called remote radio head. It is rather small in size and generally no larger than 2 feet by 1 foot by about 6 inches. The remote radio head is connected to the main digital portion of the base station through a fiber optic link. This helps to reduce coaxial feed line losses, increase system efficiency, and provide a high level of flexibility in the cell site construction. Remote radio head is one of the technologies that help to address the challenge of HEPNET market. We will talk more specifics on remote radio heads a little bit later during the course of this webinar. Moving on to the next slide. If we look at the evolution of wireless technologies, we clearly see the 5G having a number of advantages in terms of speed, bandwidth, and coverage. 5G, which is the next evolution of cellular communication technology, is the technology that is expected to bring the IoT to life. Moving on to the next slide. In addition to the arrival of massive MIMO, or multiple input, multiple output antenna technology, the introduction of new waveforms to address the limitations of OFDM and a move to millimeter wave for more spectrum, 5G is also expected to translate into significant densification of wireless networks as well as more HEPNET. I would like to touch upon how the wireless networks of the future will look. In my opinion, the small cell HEPNET approach is expected to play a significant role in improving coverage and capacity of the future mobile networks. Looking to address the staggering growth in mobile data, operators plan to lower the number of devices and users per cell, especially in high traffic areas. Already deployed for 4G LTE, mobile operators hoping to place small cells on various city structures, and they are now considering HEPNET as an essential for 5G networks, so mainly due to the number of devices expected to be connected to the internet in the future. With the arrival of the Internet of Things, 50 billion of devices are expected to be connected to the internet by 2020, many of which will still need consistent and reliable support from a wireless network infrastructure. Moving on to the next slide. Here I would like to share with you a piece of my recent research related to HEPNET. In front of you, you can see a revenue forecast for the small cell infrastructure test equipment market. It generated 1.6 billion in revenue in 2014 and grew at 12.2% rate from 2013. Because of the increase in small cell deployments globally, this market is most likely to exceed the 4.2 billion mark in 2022 and grow at a CAGR of 12.4% from 2015 to 2022. And we expect that most of small cell deployments are to happen in 2017 and 2018. So if you look at this chart, you can see that the market growth surges in those 2 years. And with this, I would like to hand this presentation over to Craig Stanziano.
Thank you, Olga. That was a wonderful opening. I hope I can amplify some of the information that you presented. Again, my name is Craig Stanziano. I'm with the Distributed Wireless Group. Our function basically is in the design, integration, and optimization of wireless networks, and we have a we specialize with those radio topologies that are of a distributed architecture. So let's jump right into the RRH information. So my next 6 or 7 slides, I hope to address these next points here. Why RRHs, where do they fit into the network, how are they connected, what do they look like, and maybe some of the general characteristics that or attributes that they maintain. So you've had a few moments to look at this first slide, which is good. It's kind of jam-packed with some juicy tidbits of information. So why RRHs? It basically comes down to 3 words, and you probably heard this in the real estate market, but it's capacity, 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 but maybe they use a different word. I'm going to make the assumption that the majority of the audience has a bit of an understanding of what cell splitting or sector splitting concept is, and basically in a nutshell, if you look at the graphic here on the left to where I'm describing serving area versus demand, you basically have a traditional cell site that is being broken or infused, if that's the word I'll use on my slide here, with additional capacity, basically individual cell sites that are delivering capacity to the same serving area, but significantly more. That graphic right there is basically a 9 times multiplier. We go from 3 to 27 serving cells in that same geographic area. The caption up there with the wireless service providers, mention the need for densification. This is kind of graphically what that might start to look like. The WISPs are trying to address the demand of their subscriber base, and it's interesting that the sales folks just enjoy the information or the rate of growth, but the engineering operation folks are probably terrified. It's just a very demanding situation for them, and they seem to be in a catch-up scenario. So the best way to describe RRH, it's a two-component device. You have your baseband unit, and then you have your RRH. And so the RRH, its benefits for us today are the fact that the OEMs have been able to drive that form factor to one that allows it to be strategically placed into the network and allowing it to deliver that capacity into the challenged areas. Some of the attributes of that RRH that make it successful today is the fact that one, it's offering the operators, the WISPs, NOCs, that visibility to the edge of the network, and as well as they were smart not to include a fan to allow the unit to be cooled. It's basically a convection-cooled item. I do list there some of the major DAS OEMs, and the question in our minds, at least in probably a few folks' minds, is where do they fit in today? What's going to be the future for them? And I'll get into that a little more later. So I depict what I feel the HETNet scenario is going to look like there in the central portion of the slide. You basically have multitude of devices that are working together, obviously, to allow for an end-to-end solution for the subscriber. And next slide. All right, so next part of my initial statement was, how are the RRHs connected? Olga did mention CIPRI as being one of those protocols. There are basically 2 out there that have been addressed. I think the Open Base Station Architecture Initiative, that was probably the first to the street to come out with a protocol to connect this distributed architecture together. The benefits of the OpenSI, it was more network inclusive. They were thinking it all the way through back to the core. The CIPRI was more focused on the payload delivery. So this whole concept was a truly distributed, disruptive standard, and it caught the attention of a lot of the OEMs. So much to the fact that the OpenSci standard immediately was followed up in 2003 with the CIPRI. Next slide. So here we go to CIPRI. Now CIPRI's pretty much gained the lion's share of the transport protocol for the RRH. It's being driven by some of the major OEMs. They had a vested interest in making sure that they had a viable protocol to allow for this RRH development and the distributed architecture development. It only took them a year to kind of jump into the game and compete against OpenSci, and as a result, they seem to be dominating the protocol today. Obviously, the optical link is a critical piece to the RRH solution, and we'll be seeing that garner more value as we progress these network developments. Next slide. All right, so trying to summarize these two protocols, why CIPRI, why not OpenSci? I tried to pick out some of the more salient attributes that differentiate the two, and I have three up here. You could argue there's 5 areas that show a significant difference, but the two of the 3 that I outlined really kind of make the decision to stick with CIPRI. You basically have higher data rates and an ability to code in a 64-bit environment now with the latest 6.1 release. So these are significant enhancements to allowing for that bandwidth to be extended deeper into the network. Bottom line here was that the payload, the amount of that IQ data that is streaming over that CIPRI link. The CIPRI, was focusing on that payload, was able to achieve, it says here, 13.75% enhancement over the OpenSci. So that was a big driver. The one thing I do make sure that the audience understands as well is that CIPRI, though stated as being an open standard, there are some vendor-specific attributes to it that are challenging to folks who might be interested in trying to manage or take advantage of that interface. So in a nutshell here, CIPRI wins, OpenSci came in second. It's kind of like the VCR beta scenario of years back. Next slide. All right, so what do these RRHs look like? A lot of different form factors out there. I tried to just pick a sliver of what is out there. There are a number of manufacturers. It's a very growing market space. The standardization, the CIPRI, it's allowing for there to be the ability of third-party vendors to try to produce product to allow it to be part of this rapid growth that Olga pointed out earlier. Huawei was an early adopter here in the U.S. I don't know if everyone recalls stealing or having understanding of what Sprint tried to do with their WiMAX delivery. Huawei was a big element in that, and hence their entrance into the U.S. market, at least in this RRH community. You have ALU, Samsung, Ericsson up here. Samsung's an intriguing one to me. I put a graphic below there, and they're already at an 8x8 MIMO delivery. And just to make sure everyone understands MIMO, multiple input, multiple output. It's a means of allowing for higher throughputs. You basically have redundant data streams, or maybe not redundant, but multiple data streams to basically yield a higher throughput. So here we have Samsung, and it makes sense. The Asian markets were very successful in applying the RRH solution. They had a huge demand in a very small space, and they kind of set the tone, and maybe still do, for us to follow and look to see where things are progressing. I put in there just a couple teasers. There's the Cube, which is I'll use light radio official terminology, and then you have the dot, which is Ericsson's. These are maybe not so much an RRH application, but I just want the audience to understand that I put in there, don't blink, because things are dynamic, things are changing. The Cube or the light radio is very intriguing. Here we have an active device mounted inside of an antenna. And you have the dot, which is an active device that is fed over Ethernet. So those are intriguing to understand that the market is definitely in an ever-changing format. Next slide. Okay, so I wanted to kind of pull out some of the salient attributes of the RRH. What's their operating range? Well, I've seen it from 450 all the way up to 2.6 gigs. The 700 and the 2.1 gigs have been pretty much the leaders. I think one, because since LTE and the 700 spectrum came out first here in the U.S., the drive to get that capacity, made the RRH very applicable to be first built. So. So I don't believe there's limitations in what the RRH can operate in versus frequency range. It's just a matter of market demand. What are the WISPs asking for? Multiband. Now, this is an intriguing one. I haven't seen a true multiband RRH in one form factor. I've seen them paired. I've seen multiple units put together basically to achieve that multi-band. And when I say that, you have 700 services with AWS services. So I've seen that scenario. I haven't seen it all in one package. RF power, wide ranging, 500 milliwatts up to 50 watts. The very admirable to the RRH OEMs to have been able to achieve, these higher power devices and not having to revert to a fan, which we, at least in my world, I don't like fans. Fans are very demanding on the network. Definitely impact your MTBF and your overall reliability numbers. Pre-distortion linearization, major feature of the RRH that has allowed for such efficiencies to be achieved by the amplifiers. The protocols, I've seen majority LTE UPS, I see GSM, I see CDMA. So again, agnostic to protocols, it all is going to come down to market demand. What are they asking for? Active antenna, yeah, sure. The RRH is in anticipation of this need to manage that capacity. They realize that having an ability to manage an active antenna, i.e. one that has azimuth or elevation control elements, that's something that they want to be able to support and pass through the CPRI link back to the BBU, where the NOx or even the RF engineering teams have access to control those attributes of the antenna. Obviously, diversity is a big driver on the RRH. We're talking about the MIMO, the ability to receive and transmit through multiple ports. As I depicted earlier, you had the Samsung product that's already at 8x8. I even think there's 8x8 here in the U.S. One of the WISPs, I think, trialed something out in Chicago area, maybe. I speculate there. So yeah, you definitely are at a minimum 2x2, but maximums are looking at this time 8x8, but I wouldn't be surprised we see something more than that. Multicast, simulcast. Now, I don't see this being deployed in the current RRH environment. Obviously, we're in a capacity-driven scenario, so maybe the concept of sharing that capacity over multiple units is not something that they're endorsing at this time. It might be a feature that's available, but as I alluded to earlier, where do the DAS OEM guys fit in? Well, I think it's this multicast, simulcast, and the multi-band capabilities. We do see that present in the DAS OEMs. This is a very powerful feature for them to further get that spatial constraint addressed and being able to deliver multiple services in a single form factor. Finally, topology. Yeah, just look back into the CIPRI link. I think there's a. I wish I should have. I should have listed that link here for you to check out. But yeah, they are not inhibiting any type of topology. Point-to-point, star, hub, spoke, ring. They're all in there. I think they are. The CIPRI standards group was understanding that they needed to have that type of flexibility as well. Okay, next slide. All right, I'm going to be kind of wrapping it up with this one. So, I depict a CRAN architecture on the left and what I'd like to refer to as the virtual RAN on the right. So, the CRAN, I think, is going to show its promise here in the next few years. It's definitely going to offer scalability to this densification of the network, manageability, reliability. You're definitely going to start seeing those benefits out of the CRAN architecture. Is it the, I like to say the cat's meow or the ultimate network solution? Maybe not. I think the network demands are way out in front of, or excuse me, the subscriber demands are way out in front of what the network topologies are. And I think we're going to be looking more and more to this more virtualization of the RAN network, the ability to have dynamic capacity allocation anywhere on the edge of the network. And this graphic really resonated with me. It came out of Dolly Wireless, one of the OEMs, the DAS OEMs, and it really resonated with me. The concept of what was macro and what's virtual. It just gave me the understanding of what the networks really have to be looking to drive to. And so I would like to say that that completes my presentation, and I guess it'd be Jeremy from Ruby Schwartz up next.
Yes, thanks, Craig. That was a great overview for remote radio heads. Very nicely done.
Thank you.
I'd like to keep the ball rolling here by discussing a number of different challenges that technicians face out in the field to test remote radio heads. We can break these issues into several categories, so I'm going to start with some common installation problems that are seen out in the field. To begin, the name of the game with testing these remote radio heads is being able to see what the remote radio head can see. This is enormously helpful in applications such as interference hunting, but it's also a very simple debugging technique that potentially prevents tower climbing and increased maintenance costs. And what I mean by this is a field technician will first perform a sanity check to verify that the remote radio head is communicating correctly at all. It's possible that the DC power wasn't hooked up correctly, for example, to the remote radio head in the first place, or maybe the fiber was connected to the wrong CIPRI port. By being able to communicate with the remote radio head and simply seeing the spectrum, that means there's a good chance everything was hooked up correctly. And as we know, a remote radio head is typically placed on the antenna mast or even integrated with the antenna itself. And this is to reduce power losses in the cabling between the remote radio head and the antenna, which is great, but not being able to communicate with it at all is a big issue. And this is a more typical scenario that we see out in the field, which could be due to one of the aforementioned issues with DC power or connecting to a wrong port, but it could be something tougher to decipher. First, there are many CIPRI versions and interfaces out there. There's really not just one flavor anymore, and there can even be proprietary CIPRI interfaces that must be supported. In addition, remote radio heads are supplied with data from the base station by means of fiber optic cables and with power by means of shielded copper cables. A major difference to the installations we're used to of corrugated coax cables lies in the fact that cables for remote radio heads cannot be terminated in the field, meaning that factory terminated cables cut to the correct length need to be provided for installation at each base station. It's imperative you have efficient logistics channels and local production facilities, so as you can tell, some good planning is required here. We also have to consider how all the equipment is physically set up. Distances between a radio equipment controller and the various remote radio heads typically range anywhere from a few meters to a few hundred meters. Keep in mind that in rural areas, the separation can be considerably greater. And because remote radio head testing requires that the radio equipment controller sends defined test signals, field tests can become very complex quickly, as well as time-consuming and costly when that REC is located far away. This drives the need for a portable simulator that can be directly connected to the remote radio head under test to save time and manpower, instead of having a one-box-fits-all type approach. And lastly, remote radios have different kinds of cables that simply aren't plug-and-play with each other. Instead, adapters are required, and faulty connections can lead to issues very quickly. Technicians must be aware of over-voltage protection-related issues that are, again, they're power and cable-related. Next slide, please. Of course, external problems, such as interference and weak GPS signals, are always relevant when we're talking about RF field testing at a base station. As I mentioned before, having the ability to see what the tower sees is extremely useful when you first go out to start interference hunting. If a technician is receiving reports that a particular sector is being affected by interference, it's imperative to have an idea of what the spectrum looks like. Many common types of interference can be quickly identified by just looking at the spectrum signature, as many of us know. And this is not to mention, this same interference could be affecting the remote radio head and or the tower itself. And then the last part I want to cover here, and arguably most important, is some special problems to be aware of with respect to the coax and antennas at the top of the tower. These days, installations with only 3 remote radio heads have now become the exception rather than the rule. In fact, 6 to 9 remote radios per site are now commonplace. And in today's networks, we can set things up with up to 5 remote radio heads per sector, meaning you could have 15, maybe more remote radios on each mast. Traditionally, each one of these remote radio heads is connected separately using a pre-connectorized fiber optic cable as well as a power supply cable, and every single one of those must be tested in the field during installation. It's common to see bad jumpers, high return loss, PIM, diversity imbalances, and more on the antennas at the top of the tower. And I'll tell you, these are the type of issues that really bog down an installation process quickly. At the end of the day, avoiding these issues with proper planning is the best way to go, but we know things happen, and when they do, it's great to be aware of what to look for. Thank you, everyone. At this time, I'd like to hand things over to Roger from Absolute Analysis to discuss the typical test workflow for field installation of remote radio heads.
Thanks, Jeremy. It's a great explanation there. You can see the life of a cell tech is quite complicated. These remote radios are provide the throughput that consumers need, but they do involve a level of complexity that is much higher than in previous generations of air technology. So what I'm going to talk about in this section is how do we find those problems for remote radio heads or remote radio units. I want to give a shout out to anybody who's using Ericsson equipment that they use the terminology RRUs. I'm going to talk about an installation methodology that's new according to how the architectures are evolving. And they're new because simply there wasn't a mechanism to be able to do these types of tests before, but they're quickly becoming very important in the installation and maintenance of either DAS networks, CRANs, or even macro cells. So the 3-step installation I'm going to talk about here is first is the physical layer. And when I mean the physical layer, I mean testing the power cables, the fiber cables, even testing the SIPRI physical layer. I can bet that most of the people on the call are very familiar with what a physical layer testing looks like. And so in this presentation, I'm not going to go into those details. What I am going to go into is the 2nd step and the 3rd step. And the 2nd step is what I call RRH or RRU polling. And the 3rd step is being able to do a basic RF test across your remote radio head. And so in these 2 steps, these are the 2 steps that are new and involve concepts of the radio head that have been talked about with Craig, and Jeremy pointed out the problems that most people who are needing to maintain the installation and performance of the new networks have to be aware of. So let's go to the next slide and we'll talk about step 2 in detail, polling. And so the first thing I want to define is what do I mean by RRH polling? And when I say polling, I mean simply just talking to the radio head and polling it for information. And the goal is to really test, is that radio head really alive? Because when you do a cable test and you do a fiber test, You can test the integrity of the cable and the connections, but you can't necessarily test whether the radio head has A, survived the transit to the macro cell tower, and B, has survived the installation process of hauling that thing up the tower or wherever the final location of that remote radio head ends up. And so if our goal is to see if that radio head is alive, the easiest way is to poll it for information. In the installation process, you oftentimes do not have the base station unit available. And if the base station unit is available, that polling process is quite easy, but it's quite difficult if you're still in the installation process and the BB integration team has not come in yet. That offers some advantages for people who are looking at doing these installations efficiently, where if you've got equipment that can pull the radio head and not have to worry about bringing the base station installation team, you'd like to fix those problems before that team comes in. So if you pull the radio head, there are two basic pieces of information you can gather. The first one is simply SFP information. So you can talk to the radio head and you can ask that radio head, what does the SFP that is plugged into your SFP cage look like? And you can obtain the manufacturer information, the serial number. The two most important things from an installation perspective on the SFP information is the speed rating. So let's make sure that the link speed matches what the SFP rate is rated for, and the temperature. So that might be an external thingy where if the temperature outside is either too cold or too hot to the rating, that won't work. Or the radio head SFP cage has been damaged somehow and the temperature is being generated internally. So that's the first piece of information you can gather. The second piece of information is a little bit more important, and it pertains to the manufacturer information. So you can ask that radio head, what's your manufacturer information with regards to the unit name or the unit number, the serial number, or the firmware revision. This type of information is dependent upon the manufacturer of the radio head. So obviously this will differ according to the manufacturers, but the basic information is still there. So if you use a piece of equipment like what I've shown here is the Integris tester, you can gather that information, make sure your radio head has been installed properly. Then we go into step number 3, which is on the next slide. And step number 3 relates to a basic RF test. So now that we've tested in step 2 that the radio head is actually alive, the very last piece of testing that we need to do is to make sure that the radio head can transmit. And so that involves being able to control the radio head to be able to send out transmission, to be able to adjust the power up or the power down, and to check for the results. Now let me explain that a little bit more in detail, because it's very important in an installation procedure to understand what not only the radio head can do, but what the external RF environment is, just as Jeremy explained in the previous section. If we can control the radio head and do these things, either with the base station or with the tester, you'll obviously also need a spectrum analyzer to measure the transmission that's coming out in the downlink. And so I've got an example of a spectrum analyzer measuring that. Now what this does is, when you're able to do a basic RF test, is it finds problems and ensures that the radio head can actually transmit, the antenna is connected properly to the coax, and the antenna is also operational. So this completes the entire physical realm of making sure that the installation of the radio head is intact and it's working. However, when you do this, you can also do a complete test, get that RF profile so that you can do an implied PIM analysis and a diversity imbalance analysis. And so let's look at an example of that in the next slide. And I'm going to use a simple macro cell as an example. In a simple macro cell, if you've got an alpha sector, a beta sector, and a gamma sector, and I'll just assume, just simply for its example's sake, that we've got 2 transmit and receives for each sector. Now what can happen is, if you're able to control that radio head and you can turn up the power, measure those results across each of the sectors, and then turn down the power and measure the RSSI in the uplink on the low power, you can collect all of the information across each of the transmitters and receivers across each of the sectors. And what that will do, and again, this is just an example, if I look at the beta, if I look at the alpha sector here, the alpha sector is very nominal. The uplink RSSI power remains relatively stable according to the downlink power adjustments. However, if you look at the beta sector and you look at transmit number 2, if you've turned high power up on either of those transmits and it causes the uplink power to rise significantly, then you can make some assumptions that you've probably got some kind of problem, either an applied PIM problem or a diversity imbalance problem, which may be an external RF thing or it may be an equipment malfunction. So that is the indicator for the technician to say, okay, I now have a problem that I gotta go solve, and it's immensely helpful to be able to do that before the base station integration team comes in. And so I know a table might tell you a little bit more, but we've got a real-life case study in the next slide that really signifies the old adage that a picture is worth 1,000 words. So in a recent macro cell that we were assisting the service provider on, there was a condition on the left where we've got the downlink power turned very low, and we looked at the uplink spectrum, and the uplink spectrum looked very nominal. However, if you look to the right, we turned the downlink power on high, and now the uplink spectrum looks not good. I don't know what the scientific term for this, but it's not supposed to look with such a high noise profile on the right side of the graph. So now we know, and this actually turned out to be an internal equipment problem. They had a bad antenna. And so this has at least alerted the technician to equipment problems that were still able to be solved before the base station integration team came in. So this is just a good example and a good picture of what an implied PIM case study might look like. So we can go to the next slide, and you know, the webinar is approaching up to the 45-minute mark, so I really didn't have time to dive into the details, but if I summarize the whole RRH RRU installation testing methodology, we have step 1, looking at the physical layer, and a lot of the technicians and the operating procedures already account for this. We have step 2, which is the RRH RRU polling, and then we have step 3, just doing a basic RF test to test for the very last part of the tower and to test for external RF problems. And in this case study, I have a couple of references at the bottom. We use the Integris product from Absolute Analysis, and we use the Rode FSH3 from Rode & Schwartz, the spectrum analyzer. So that is a summary of the testing methodology that I've proposed, and I will hand it back over to Olga for the final wrap-up.
Thank you, Roger. I just want to make a few final conclusions and kind of summarize what has been said during the course of this webinar. Exploding mobile data and smartphone adoption rates will continue bringing in new technologies. There's no question about that. And mobile operators are aggressively and proactively leveraging advanced optimization technologies to ensure better and reliable coverage. With the mobile data growth increased by IoT, 5G is expected to improve data bandwidth, decrease latency, and increase network capacity. Radio access networks have evolved significantly from the traditional macro access networks of the past, and today the ability to address network issues around capacity, coverage, and quality in a more cost-efficient way became the reality with the effective implementation of small cells, distributed antenna systems, and remote radio heads. The wireless industry has been increasingly moving to distributed base station architecture, as we all seen today. And with the remote radio heads, because of their better performance and overall cost savings, which are needed for 4G LTE network speeds and satisfying today's mobile users' requirements. So there's a number of different challenges faced in the field when testing remote radio heads. As we heard, they are cabling, jumpers, antennas, swapped connections, interference, and other incompatibilities. They can lead to time-consuming testing efforts that could be very costly. So the proper planning is the most effective, but going forward, having a good idea of what to look for when things go wrong is the key. And with this, we will open the floor for the questions.
All right, great, everyone. This is Kyle again. Great presentation. So we've had a number of questions come in, so we'll have time to get to just a couple of them. So let's jump right in. Craig, first one to you is what type of the interface connectors do we use to connect the fiber between BBU and RRH? As far as what type of dark fiber, single mode, or multi-mode?
Sure. You're going to find your dependence being driven by the optical transceiver that you're looking to deploy. So what does that mean? Well, optical transceivers, they come in a number of different types. You can, depending on your deployment, if you need longer range, you can do single mode. If it's a shorter range type of application, you do multi-mode. You can have duplexing post transceiver if that's even something if your backbone is limited in fiber counts, you can look at muxing the wavelengths. As far as connectors, I think the typical one today is the LC UPC. It's pretty standard, but I have seen LC APC.
Okay, great. Next question, Olga, on slide 11, we had a question. So is all test equipment RF and optical, including CPRI? Hi, Olga, can you hear us?
I'm sorry. I think I was on mute. I'm sorry. So the scope of the study is R&D and field test, and we did cover only RF portion of it. So on the both sides of things. So we're looking at the RF generators, analyzers, conformance testers, base station test equipment, and on the field side, we're looking at handhelds and as well as drive test equipment.
Okay, great. Next question, I think Jeremy would be best sent your way. So as Craig pointed out earlier, CPRI spec allows for more vendor-specific information. How does a tester handle various remote radio heads from different vendors?
Well, I think you have to do research into the equipment itself and all the standards and protocols that are in there to make sure that everything is supported. I might actually defer a little bit to Roger as well. He might have some insight there too. Roger.
Yeah, the real trick on understanding CPRI, and sometimes the C in CPRI stands for common, but our engineers like to use that C and say custom, because within a spec, you can actually allow customization within the parameters of the spec. And so within test equipment, you just have to know what the characteristics of the different manufacturers are, and what we do in our test equipment is we set profiles. So there's equipment manufacturer number 1 is going to have a profile, and equipment manufacturer 2 is going to have a different profile. But yeah, you really have to understand what they do.
All right, great. I think we have time for about one more question. So, Roger, so as RF coax is replaced by fiber from the RF source to the final stage amps, what kinds of RF over fiber test equipment are needed, as well as training?
Yeah, so it is a different paradigm, and all the technicians I've worked with is a mixed bag. A lot of them will understand the concept of fiber, maybe from previous training or previous experience. but there is also some who will not understand any concept of fiber testing at all. So my recommendation, and I think other test and measurement equipment vendors are following, is to provide training on fiber testing, whether it's RF over fiber or command layer commands over fiber, or just simple fiber testing. I do think that there will be a big industry need for training.
All right, thank you. So that's about all the time we have. Just a reminder to everyone in the audience that after this webinar, once I get everything processed, I will be sending out a link to the recording of today's webinar as well as a PDF of the slides. Also, all of our participants today will receive a copy of the questions for any that we did not get to. So I want to thank everyone for attending today's webinar, Remote Radioheads in Today's Evolving RAN Environment, sponsored by Rodian Schwarz. Again, our presenters today were Craig Stanziano, President of the Distributed Wireless Group, Jeremy Klein, Applications Engineer at Rodian Schwarz, Roger Pahe, VP of Product Strategy at Absolute Analysis, and Olga Yashkova-Shapiro, Program Manager, Communications Test Practice at Frost & Sullivan. Thank you, everyone, and have a great day.